above a quiet neighborhood. The moon looks familiar, yet its bright face still asks unfinished scientific questions tonight. Through a backyard telescope, that distant world becomes personal, close enough to recognize, but not close enough to understand. The lens pulls us from porch light and glass into a cratered place no backyard can ever soften. What seemed like a smooth silver disc becomes a battered landscape of rims, scars, shadows, and ancient collisions. Even the dust is not decoration. It is sharp lunar history ground into fragile gray, glassy fragments underfoot. A footprint proves humans arrived, but one step cannot explain an entire world still hanging silently above Earth. Beyond the landing sites, black crater shadows hide places colder and less familiar than the night sky suggests. The moon is close enough to shape our tides, yet extreme enough to remain another world, entirely above us. To understand it now, we have to leave nostalgia behind and follow the evidence across its surface carefully. Apollo touched the moon in remarkable places, but those points were tiny against the whole nearby lunar globe. On the Sea of Tranquility, Apollo became humanity's first careful doorway into another world's physical evidence for science. Beside the lander, an astronaut's body suddenly made the moon feel human, sized, fragile, and exposed beneath black sky. One preserved footprint says we arrived, but it also shows how little ground we actually touched there ourselves. Pull back from that print, and the landing site nearly disappears into a vast gray plain beyond him. Apollo explored real lunar ground, but mostly near side locations chosen for safety, access, and mission limits on the surface. When astronauts sealed rock samples, pieces of the moon began answering questions back on Earth in careful laboratories. After splashdown, the mission kept unfolding in microscopes, seismograms, and quiet rooms of patient analysis for decades afterward. Inside the rocks, scientists found clocks, heat records, and impact clues older than any city on Earth today. But one sample tray can never speak for every mountain, basin, and shadowed crater on the moon alone. So the investigation had to grow from landing sites into a global portrait of the moon far beyond those first footprints. Rovers stretched human reach across rough terrain, following clues no bootstep alone could have covered during brief missions. For astronauts, those drives were ambitious. Across lunar geography, they were only careful short neighborhood walks at best. Mission paths followed time, safety and science limits, not a complete map of lunar possibility for future explorers. Each landing site carried its own story, while the rest of the moon waited mostly unseen beyond frame. Fractured rocks hinted at impacts, buried heat, and old processes written in broken mineral textures seen up close. Instruments left behind turned silence into signals, extending the mission after astronauts had gone home to Earth again. Those signals revealed patterns beneath the surface, yet each pattern still depended on limited coverage for useful science. Some lunar questions remain difficult because the moon was measured unevenly, not because science stopped asking new ones. Decades later, researchers still compare old readings with new images, building answers from scattered clues carefully every year. Across enormous regions, no rover tracks, drill holes, or astronaut footprints have ever crossed the ground directly on site. Modern orbiters return to the moon like quiet detectives, patiently mapping regions boots had never reached from above. From orbit, instruments can read height, chemistry, and gravity, turning distance into a new kind of fresh evidence. The bright highlands and dark plains do not tell the same story about lunar history everywhere across the moon. A crater may seem small from Earth until its rim stretches farther than a city drive back home. The moon has layers and a core, but probing them is harder than studying Earth's interior from here. Seismic vibrations gave scientists another tool, turning faint lunar shaking into clues about hidden structure deep below inside. But the Moon's interior cannot be photographed directly, only inferred from signals that pass through it quietly over time. A world can look perfectly still from orbit while preserving ancient stress inside its cold crust below the surface. New images force old assumptions to move, which is how careful science keeps the story alive over decades. The next clues are not in footprints, but in scars blasted across the moon long before humans arrived. Apollo gave direct evidence from real ground, but direct evidence still came from selected places alone, not everywhere. Against the entire lunar globe, every visited site becomes a pinprick on a vast map hanging near Earth. The unvisited moon may preserve answers that no return sample has yet been able to carry back home. A crater is not only damage, it can be a timestamp, a witness and a warning still today. In a flash of ancient glass, Apollo evidence opens toward a much older lunar violence archive beneath us. Here, the moon becomes less a destination than a witness to the solar system's violent beginning near Earth. When objects struck the young moon, they carved basins, shattered rock, and rewrote the surface over deep time. One crater leads to another until the landscape becomes a record too large to read at once clearly. Younger scars overlap older ones, helping scientists reconstruct sequence without pretending every date is settled completely or exactly. Earth erased much of its early violence, but the moon kept the scars in plain sight above us. The camera leaves the rim behind, revealing craters nested inside craters, like scars layered across an ancient desert. Each circle marks a collision, but together they form a record Earth can no longer keep on its surface. On Earth, rain, wind, oceans, and moving plates erase impacts that remain almost frozen across the lunar plains. The moon became a kind of archive, preserving violence from a time when the solar system was still young. A small crater may look simple, until its shadow reveals broken walls, melted rock, and scattered bright debris. From above, the landscape resembles a battlefield without sound, where every mark was made by falling stone. But these craters are not just damage, they are timestamps written into rock, dust, and frozen sunlight. Scientists can read the overlap of rims because younger impacts cut across older ones like fresh tire tracks. A new crater does not politely avoid the past. It punches through earlier history and leaves a clue behind. By following those clues, lunar geology becomes a detective story told through circles, shadows, and broken stone. The view pulls wider, and a crater no longer feels like a hole, but part of a larger pattern. Some impacts were so immense they shaped entire basins, regions wider than many American states laid side by side. If a basin like this were placed over Earth, it could swallow cities, highways, and whole mountain ranges. The moon keeps those giant scars visible, while Earth's own ancient wounds were recycled by a restless planet. This is one reason scientists study the moon to understand what early Earth may have once endured. The same bombardment that battered the moon also struck Earth, but our planet healed, drowned, and buried the evidence. Lunar rocks brought home by Apollo became more than souvenirs. They became fragments of a vanished era. Inside those samples, minerals recorded heat, shock, and time, like pages torn from the solar system's childhood. Yet the samples came from limited places, leaving much of the moon's global story still partly unread. A rock from one landing site cannot explain every basin, every lava plain, or every buried layer. Orbital maps help fill the gaps, but distance can still hide details only ground instruments would catch. The camera glides over dark volcanic plains, where ancient lava once pooled inside massive impact basins. These dark regions, called Maria, shape the familiar face Americans see from backyards and city streets. Their smooth appearance can be misleading, because beneath the calm surface lies a history of fire and impact. Here, the moon challenges a simple belief. It was not always as still as it appears tonight. Long ago, Heat inside the moon helped feed eruptions that resurfaced parts of its battered face. Those eruptions did not make the moon Earth-like, but they prove its early interior was not inactive. The question is not whether the moon changed, but how much of that change we can still reconstruct. A close view of cracked basalt shows that even dark plains hold evidence of cooling, stress, and time. Every texture matters because lunar geology often hides its biggest clues inside the smallest surface details. Impact glass, tiny beads, and shocked minerals can reveal temperatures no living world could casually survive. Under a microscope, a grain of moon dust may preserve a collision older than any human civilization. At this scale, the moon stops looking empty and starts looking densely written, line by line. But reading that writing is difficult because the lunar surface has been churned for billions of years. Micrometeorites keep striking the ground, slowly gardening the soil and mixing layers that once formed separately. That constant bombardment makes the surface both an archive and a puzzle with many pages shuffled together. A fresh impact can expose material from below, briefly opening a window into hidden lunar layers. For scientists, those bright rays are not decoration. They are trails leading back to excavated material. Some rays stretch for hundreds of miles, crossing older terrain like pale brushstrokes on a dark canvas. Following them can reveal how far violence travels when there is almost no atmosphere to slow it. Without air, incoming rocks strike the moon at brutal speeds, turning motion into heat, glass, and dust. There is no wind to soften the blast, no rain to wash the new scar away. The result is a world where destruction can remain visible long after Earth would have forgotten it. That preserved violence gives the moon scientific value far beyond its quiet appearance in the night sky. It may help scientists estimate how often large impacts threaten the early Earth and other rocky worlds. Still, the record is incomplete because each new mission can revise how older evidence is interpreted. A single crater age, measured more precisely, can shift the timeline of an entire bombardment story. This is why the moon remains unfinished science, not despite Apollo, but because Apollo opened the archive. The camera settles on dry gray soil, where ancient history seems silent until a different question appears. If the moon looks so dry, why do modern instruments keep finding mysterious signs of water? The moon looks dry enough to end the question, yet its dust began raising a harder scientific mystery. At ground level, the surface seems empty and powdery, like a desert with every trace of moisture removed. But laboratory instruments can notice chemical fingerprints that human eyes would miss on this silent, gray surface. Those fingerprints do not mean puddles or frost. They may mean water molecules, hydroxyl, or related chemistry. Across a whole lunar landscape, even tiny traces can become important when the ground stretches for miles. From orbit, instruments read reflected light, searching for subtle clues hidden inside the moon's dusty skin. The evidence does not paint one simple moon, but a patchwork of places behaving differently over time. A rover crossing this plane would not be looking for lakes, but for chemistry beneath its wheels. Regolith may look like blank powder, yet every grain carries a history of radiation, impacts, and reactions. Once water, related signals appear, the next question is harder. Where could that chemistry have come from? Could sunlight, solar wind, and exposed minerals be quietly changing the surface one particle at a time? Hydrogen from the solar wind can interact with oxygen, bearing minerals, creating chemical hints without making liquid water. Then, tiny impacts disturb the dust, heating grains and scrambling the chemistry in brief, violent flashes. Each strike may release, bury, or move fragile molecules before the surface settles back into silence. The moon's long day and night create brutal temperature swings that can change where molecules survive. Instead of flowing like a river, some molecules may hop across the surface, moving in fragile steps. But movement does not mean abundance, and abundance does not automatically mean a resource astronauts can use. To know the difference, future explorers need measurements taken directly from soil, shadow, and drilled samples. A rover's drill turns the mystery from a distant signal into a physical test of lunar ground. That test points toward the poles, where darkness may preserve clues the sunlit plains cannot keep. Near the lunar pole, low sunlight stretches shadows across crater rims, turning terrain into a maze. Driving into permanent darkness would challenge cameras, batteries, navigation, and every assumption made in daylight conditions. Inside those shadows, extreme cold may act like a trap, holding fragile volatiles for immense spans. A cold trap is not magic, it is a place where sunlight cannot easily erase the evidence. Some lunar shadows may be colder than Antarctica, turning familiar cold into something far more alien. Orbital maps suggest some polar regions may be richer in hydrogen-related signals than surrounding terrain nearby. Yet an orbital signal is still indirect, and it may hide depth, purity, or confusing mixtures. Only drilling into the surface can show whether the signal is shallow, buried, scattered, or concentrated. The sample might not sparkle like ice. It could appear as ordinary dust with unusual chemistry. So the real question is not just whether water exists, but whether humans can actually reach it. For future missions, water matters because it touches drinking, breathing, cooling, farming, and rocket fuel chemistry. Split into hydrogen and oxygen, water could support life systems and help make propellant beyond Earth. But a useful idea on paper can become brutal when the resource is frozen, buried, or diffuse. The worksite may combine darkness, extreme cold, rough slopes, weak communications, and limited power at once. A single water bottle feels simple on Earth, but on the Moon every ounce becomes logistics. Extracting water would require drills, heaters, storage tanks, power lines, vehicles, and constant dust control systems. An astronaut near a shadowed crater would see little beyond suit lights, gray slopes, and blackness. The best landing site must balance ice clues, sunlight, safe slopes, communication, and room to operate. Water is only useful when scientists know its amount, depth, purity, form, and surrounding hazards clearly. That is why the water question becomes a survival question before it becomes a settlement dream. The evidence chain begins above the Moon, with orbiters measuring signals no astronaut can see unaided. Different instruments detect different clues, like reflected light, neutron patterns, temperature, or subtle surface chemistry changes. Even strong signals can leave the hardest questions unanswered: what form, how deep, and how much. Ground truth begins when a lander touches down and compares the orbital promise with actual soil. Below the first dusty layer, the Moon may hide patterns that orbiters can only suggest indirectly. A laboratory instrument can separate trapped molecules, mineral bonds, and contamination possibilities with far greater care. A small polar deposit could reshape mission planning across Earth, lunar orbit, and future deep space routes. Future missions are not just returning to the Moon, they are testing whether promise becomes proof. The water story is unfinished, but it is not imaginary. The clues are real and demanding. If water behaves differently across the Moon, what does that reveal about the whole lunar world? A signal connected to water is evidence, but it is not the same as a drinkable pool waiting there. From orbit, spacecraft read reflected light and chemistry, searching for clues too faint for human eyes alone. The surface may look bone dry, yet molecules can cling to grains like dust on a desert windshield. A trace in one scoop of soil can reshape plans for rockets, habitats, and entire lunar supply lines. The harder question is not whether clues exist, but where they gather and whether astronauts can reach them. Inside permanent shadow, temperatures can preserve ancient ice, but darkness also hides the evidence from easy view. Radar and infrared maps hint at patterns, yet each instrument sees the moon through a different kind of filter. A bright patch on a map may be promising, but promise is not the same as confirmed ground truth. Before anyone mines lunar ice, a rover must prove what is actually mixed into the dust. The water story ends not with certainty, but with a cold region pulling the investigation southward. Near the lunar South Pole, sunlight skims the ground so low that shadows stretch like frozen canyons. The landscape is not a smooth landing field, but a maze of crater rims, slopes, and hidden hollows. Some crater floors may not have seen direct sunlight for millions, perhaps billions, of years at all. In those black interiors, cold can trap molecules the way a deep freezer holds forgotten ice. But a place that preserves ice can also defeat cameras, power systems, and careful human judgment. A rover entering shadow would trade sunlight for silence, cold, and a narrow cone of artificial light. Along nearby ridges, solar panels might find power, while the resources may sit lower in darkness. That split creates a lunar dilemma: live near the light or work where the cold traps are. From orbit, the South Pole looks like a puzzle of bright edges and bottomless dark pockets. Every possible landing site must balance science, safety, communication, sunlight, and the slope beneath the legs. A crater rim can shine for long periods, yet one wrong descent could drop machinery into darkness. The moon offers no weather forecast, but its shadows create hazards as unforgiving as any storm. Inside the shadow, a headlamp may reveal only dust, broken rock, and the next uncertain meter. Extreme cold changes the problem from exploration to survival, especially for batteries, joints, and exposed instruments. The coldest places are scientifically valuable because they may have collected material from comets, asteroids, and solar wind. Those deposits could be a frozen record, not just a resource for future rockets and habitats. A sample from the darkness might reveal where lunar water came from and how long it stayed. Yet collecting it requires touching a place designed by nature to keep heat and light away. The South Pole is not mysterious because it is magical, but because the conditions are so hard to measure. Each shadowed crater becomes a question mark, cut into gray terrain and protected by ancient cold. Above the shadows, sunlit ridges could power a base, but they may not hold the best samples. Below the ridges, possible ice waits in darkness, separated from power by rough and risky ground. A future crew might see sunlight overhead, while their most important target stays hidden far below. That contrast turns the South Pole into an engineering problem wrapped around a scientific mystery underground. Mission planners study angles of sunlight the way hikers study weather before crossing a dangerous pass. A few degrees of slope can decide whether a lander stands safely or never works properly. Communication also matters because Earth hangs low or disappears behind terrain in some polar locations entirely. A relay satellite may become the invisible lifeline between a shadowed rover and controllers back home. The moon is close to Earth, but at the pole, closeness can feel strangely misleading to explorers. Every advantage has a cost. Light means power, darkness may mean ice, and distance can mean silence. The deeper the camera looks into polar darkness, the more the moon stops feeling familiar again. What seems like a simple gray world becomes a landscape of traps, trade-offs, and unfinished measurements. Future astronauts will not just plant flags there, they will test whether our maps are good enough. A base near the South Pole depends on answers that still sit inside permanent shadow below. If ice is scattered thinly, the dream of local fuel becomes far more complicated for crews. If richer deposits exist, they could change how humans move through the inner solar system someday. Between those possibilities lies the honest uncertainty that makes lunar exploration still scientifically alive for scientists today. As the camera rises, the polar terrain becomes a ring of light around unresolved darkness below. Beyond the rim, Earth sinks toward the horizon, and the moon begins to feel less like a neighbor. The next mystery is not in darkness at all, but on the side we almost never see from Earth. At the crater rim, sunlight grazes the surface, while the interior below remains almost completely black. Inside that darkness, even a small rover would depend on its own lights to read the ground. If ice exists here, it may hide in scattered grains, not in bright sheets waiting to be found. These shadows are not magic. Low sunlight and crater walls create pockets the sun never reaches. A single shadowed basin can stretch wide enough to turn exploration into a slow, cautious search. From orbit, instruments can hint at ice, but only groundwork can confirm what is actually there. Cold, darkness, broken terrain, and weak communications can turn a promising crater into a serious mission risk. The moon's most valuable places may be the places our eyes and cameras struggle to understand. Polar maps mark possible cold traps, but every colored patch still needs careful confirmation on the ground. So the real question remains simple: what will future missions actually touch inside these frozen shadows? As the camera rises from the pole, the darkness becomes part of a much larger lunar puzzle. From orbit, the shadowed craters are no longer isolated pits, but pieces of the moon's geometry. Some hidden places are made by sunlight and terrain, while others are hidden by the moon's motion. From any backyard telescope on Earth, we keep seeing almost the same familiar lunar face every month. The far side is not hidden by endless night, it is hidden by a slow orbital lock. Now the view drifts around the moon's edge, toward terrain earthbound eyes never directly see from home. Tidal locking keeps one hemisphere facing Earth because the moon's rotation and orbit are synchronized over time. The far side has day and night too, but Earth never gets a direct front-row view. When the two hemispheres are compared, the familiar near side looks smoother, darker, and strangely different. Why should two halves of the same moon carry such different scars across their ancient surfaces? The far side appears rougher, brighter, and more heavily cratered than the face we recognize from Earth. Here, small craters become part of a larger impact record written across entire lunar regions over time. The near side holds broad dark volcanic plains, while the far side has far fewer of them. Far side highlands may preserve a crustal story that near side lava flows partly covered and simplified over time. One leading explanation points to crustal thickness, which may have limited volcanic flooding on the far side. So the far side is not merely unseen, it may preserve a different chapter of lunar evolution. Its rugged terrain would make landing harder, with boulders, slopes, and crater rims threatening every approach. A mission here would need sharp maps, careful navigation, and communication support beyond the lander itself. That same isolation creates a practical problem for engineers and an unusual opportunity for scientists on Earth. What could we hear from the far side if Earth's constant radio noise finally disappeared below the horizon? The far side can be naturally shielded from much of the radio chatter spilling outward from Earth. The moon itself can block direct radio interference, creating a rare quiet zone in nearby space. A radio observatory there might search for faint signals that are nearly impossible to hear from Earth. A broad crater floor could become a natural stage for instruments larger than a football field. Because Earth cannot see the far side directly, missions depend on relay satellites above the moon. For astronauts or robots, every command would pass through infrastructure that must work before exploration begins. What makes this place difficult to reach also makes it scientifically precious, unusually quiet, and worth protecting. Future instruments might listen for ancient whispers from the universe before stars fully filled the darkness. Even there, dust, temperature swings, and deployment failures could challenge the most advanced observatory plans humans build. The silence of the far side leads back to an older question written into the rocks. Across its basins, the far side may preserve clues to ancient impacts and crustal history below. Its rough surface texture suggests repeated bombardment, long exposure, and billions of years of space weathering. The record stretches from tiny broken fragments to enormous basins large enough to reshape whole landscapes. Scientists can estimate relative ages from crater counts, but samples from the far side remain limited. The far side is not empty, it is crowded with history that has not been directly sampled. Yet that same rugged record creates hazards for landing legs, rover wheels, and human footsteps on uneven ground. Exploring it would require more than a lander, including relays, maps, power systems, and reliable mobility. The moon's geometry turns one hidden hemisphere into a test of science, engineering, and patient planning. So what could far side rocks reveal that near side samples have never been able to answer directly? The camera settles on a worn rock edge, holding the next clue beneath a crossing shadow. The far side can block much of Earth's radio noise, creating a silence scientists may finally use. It is not darker than the near side, but its battered surface tells a different geological story. Beneath that surface, crustal differences may have shaped which scars remained exposed and which lava plains never formed. The model matters because every ridge and crater still carries evidence that numbers alone cannot explain. A silent crater wall can become a record if scientists can learn which marks belong together. From Earth, the far side speaks through orbiters, relay satellites, and patient interpretation of distant measurements. A relay satellite does something simple, but essential: it lets a hidden landscape send its story home. In that radio quiet, a lunar plane could become a listening post beyond our noisy planet. If Earth's signals fade behind the moon, what older whispers from the universe might become detectable? The mystery is not darkness, it is why this side seems to remember a different history. Side by side, the familiar face looks smoother, where the far side appears older, rougher, and more battered. Deep structural differences may have guided lava on one side, while leaving the other side heavily scarred. A small rock fragment can hold chemistry that points back to enormous impacts and missing chapters. One carefully chosen sample could answer questions that orbiters can only sketch from far above today. The same isolation that protects far side science also makes every landing, signal, and rescue problem harder. Crossing a single ridge can turn the moon from a familiar face into hidden geography beyond view. Mapping did not make the moon less mysterious. It showed how uneven the whole story remains. If both sides carry different scars, the next question is what has been moving underneath them. The far side leaves a quieter puzzle. Can a world look still while stress shifts inside? A small lunar cliff may be a clue that this quiet world has not been completely still. Without moving plates like Earth's, what force could make lunar dust tremble under a frozen sky? On Earth, many quakes start with shifting plates. On the moon, the causes must be different. Earth's gravity still tugs the moon, helping load stress into a crust already cracked by time. Some scarps look like squeezed crust, leaving low cliffs across a surface that rarely erases damage. As the moon cooled over billions of years, its outer shell could wrinkle, shrink, and fracture. At ground level, one wrinkle in the crust can become a wall, a slope, or a hazard. A future habitat would not need a huge quake to worry about unstable ground nearby every day. The shaking moon is not folklore. Instruments have recorded real motion moving beneath the surface itself. A moonquake is also a signal, carrying information through rock no camera can directly enter today. Not every moonquake starts the same way, and different signals point to different kinds of stress. For future explorers, shallow shaking may matter most because it begins close to the surface itself. For astronauts and rovers, The question becomes not only where to travel, but what the ground remembers. A fracture only inches wide can still change how a boot, wheel, or instrument meets the surface. With no rain to erase it, a small scar can remain visible for an astonishingly long time. When sunlight strikes without air, rock heats and cools with a speed that can open cracks. One cracked stone is local, but the moon also answers to forces stretching across its orbit. Some signals begin deep below, while others rise from the brittle shell future crews must cross. A shallow tremor does not need drama to make loose slopes and boulders worth studying carefully. Choosing a landing site also means accepting certain slopes, shadows, ground risks, and unknown motion below. Earth builders study wind, rain, and soil. Lunar builders must learn a stranger ground language first. A hairline crack is not a disaster, yet delicate instruments can still notice tiny motion nearby. The moon's stillness makes it valuable for science, which is why unexpected motion becomes important evidence. A sensor cannot see the interior directly. It listens to motion and converts shaking into clues. When stored stress slips along a weakness, the release can travel through the crust as vibration. Above that hidden slip, the surface may show little except a landscape, quietly recording motion below. The moon can move and still look untouched, making its silence harder for scientists to interpret. A line on the horizon becomes part of a larger pattern, a world adjusting as it cools. For future crews, moonquakes are not trivia. They help decide where humans can safely stay later. The question is not whether the moon has shaken, but how well we can predict what matters. To understand the moon's future, the investigation must return to the smallest signs on the ground. Inside the crack, dust sits undisturbed, yet its sharp edges hint at stresses moving beneath the surface. The camera pulls back, and one hairline fracture becomes a scarp running across the gray plane. On Earth, cracks often follow plates, but the moon has no plate tectonic engine like ours. Instead, its ancient interior slowly cools, shrinking the surface enough to wrinkle and break in places. A fault scarp may look frozen, but it marks movement written into the brittle lunar crust. The moon also feels Earth's gravity tugging at it, stretching the body in subtle, repeating cycles. Those tidal pulls do not create oceans there, but they can add stress to fragile faults. A seismometer does not need drama. Tiny trembling lines can reveal a world still adjusting underneath. Some moonquakes are deep and regular, while others near the surface could matter more to astronauts. The quiet landscape begins to feel less like a museum and more like a sleeping structure. A shallow moonquake would not behave exactly like an earthquake, but it could still shake hardware. For a future habitat, even small ground motion becomes important when escape is hundreds of thousands of miles away. The ridge casts a thin shadow, like a cracked sidewalk stretched across an entire empty neighborhood. A rover wheel pauses near the scarp, making the fault suddenly feel like a landing site problem. The question is not whether the moon is alive like Earth, but how quietly it changes. Scientists read scarps, boulders, and dust slides as clues, not as proof of one simple cause. Some slopes show fresh material, suggesting gravity and shaking may still reshape small pieces of terrain. From orbit, these details look minor, until a planned base sits beside one of them someday. A habitat needs sunlight, water access, and safe ground, which may not always exist together there. The South Pole offers promise, but its ridges and shadows also complicate every engineering choice ahead. A seismometer beside a habitat would listen for the moon's slow settling, not violent Earth-style earthquakes below. Its readings could tell builders which places are stable and which only appear that way from orbit. The lesson is uncomfortable. The nearest world may be quiet without being completely still beneath us. A long shadow crawls across the scarp, turning the ridge into a warning line for explorers. future astronauts may cross ground that has moved before and could move again in subtle ways. No single clue explains every moonquake because impacts, cooling, and Earth's pull can all shape the shaking. That uncertainty does not make exploration impossible, it makes careful mapping part of survival on arrival. The camera leaves the fault, following loose grains that slide down toward a waiting bootprint below. The same surface that can crack also breaks into powder, covering nearly everything humans would touch. Before anyone builds there, the moon's quiet ground must be understood as both history and hazard. At first, the footprint looks beautiful, a human mark pressed into gray powder under harsh sunlight. But lunar dust is not backyard soil. It formed from impacts, radiation, and broken ancient rock. Without wind or water to smooth it, each grain can remain jagged, sharp, and stubborn for ages. A microscope view turns the soft, looking surface into glassy fragments with edges like crushed ceramic shards. This is why a simple bootprint becomes more than a symbol, it becomes an engineering clue. Dust clings to fabric, joints and tools, carried by static charge in the dry lunar vacuum. On Apollo suits, the gray coating was memorable, abrasive and difficult to keep outside the cabin. For short visits, dust was annoying. For long stays, it becomes a system-wide design problem quickly. A rover wheel rolls forward, grinding particles that can wear seals, hinges, and moving parts over time. The danger is not cinematic poison, but slow damage across equipment, lungs, and living spaces over months. Every airlock must become a boundary between exploration and contamination, between the surface and home inside. A beam of sunlight catches floating grains, making the dust look almost alive in the stillness. Unlike desert dust in Arizona, these grains have not been rounded by weather or flowing water. They can scratch, cling, and migrate, turning routine movement into a constant maintenance challenge for crews. The moon's smallest material may decide how often astronauts can work, repair equipment, and breathe safely inside. Engineers test brushes, seals, and electrostatic systems because cleaning dust may be as vital as landing. A glove flexes slowly, and the dust packed into its seams refuses to fall away cleanly. The problem feels small until every hinge, visor, and filter must survive thousands of dusty cycles. The boot lifts from the powder, leaving a crisp edge that will not soften in wind. Dust clings to the sole in sunlight, carrying the next problem toward every human machine nearby. Gray grains cling to the glove seam and metal handle, turning one touch into a lasting contamination mark. Once dust slips into moving joints, a simple hatch or tool can begin wearing itself from the inside. Lunar grains are jagged because no rain, rivers, or wind have softened their edges over time. The danger is rarely instant. It builds with every scrape across fabric, metal, and protective seals. A narrow connector may look minor, yet one dusty seal can threaten pressure, power, or communication. The problem does not stop outside. Every grain carried indoors becomes part of the habitat system. At the airlock, astronauts would fight a border war between the moon's dust and breathable air. Filters, fans, and airflow are not background details. They decide whether a habitat stays clean enough. On long missions, dust removal becomes a daily procedure, as routine and necessary as checking oxygen. In suit folds and hinge lines, the smallest grains hide where brushes and wipes struggle to reach. Each rover pass can lift a new sheet of regolith, spreading the problem across the work site. Low gravity changes the dance of dust, letting particles travel differently before settling back down again. When dust coats panels or sensors, it can quietly steal power, accuracy, and confidence from instruments. A science package is only as reliable as the clean surface it needs to read the moon. A dusty visor turns the hazard personal, narrowing the world an astronaut can safely see during work. In a landscape with few landmarks, reduced visibility can make every step and turn more uncertain. landing engines can throw regolith outward, turning one spacecraft event into a wider contamination problem nearby. Where a base places roads, pads, and instruments may depend on how dust moves under thrust. Dust control begins before astronauts arrive, with layouts that separate clean zones from disturbed ground safely. A prepared landing pad could help, but building one means hauling, processing, or shaping lunar materials. Even with controlled zones, the moon keeps pressing dust against every boundary between outside and inside. The concern is not only machinery. Fine particles inside a cabin could affect human health over time. Risk depends on particle size, exposure time, and whether filters can capture what crews breathe daily. A small dust leak becomes larger on missions where the same tasks repeat for months together. Over time, dust is not just a hazard, it becomes maintenance, schedule pressure, and mission cost. The famous footprint is beautiful, but it also reveals a surface that remembers every human disturbance. Regolith is not a patch around one landing site. It is the ground of the moon. Any permanent habitat would live inside that dusty world, not beside it or above it safely. A dust plan must connect suits, rovers, airlocks, filters, and repairs into one working system safely. On the moon, a base is not a building, it is a chain of dependent protections. Solving dust only opens the next question, because the surface is exposed in many other ways. Without an Earth, like atmosphere or magnetic shield, astronauts meet hazards that dust cannot explain alone there. Some of the most dangerous forces near a habitat would be invisible until instruments measured them. Radiation, temperature, dust, and power do not arrive separately, they push on the same survival system. If dust is the first test, the larger test is whether humans can stay at all. A moon base is not just construction on gray soil, it is survival engineering on an airless world. Every wall must do more than divide space, it must hold pressure, block radiation, and resist impacts. Inside, survival would feel intimate and mechanical, with every breath depending on systems that cannot casually fail. Electricity becomes life support, powering heat, communications, air circulation, lighting, and the machines that handle water. At the poles, sunlight may be valuable, yet nearby shadows can remain brutally cold and unreachable. Thermal control is not comfort. It is the difference between working hardware and a frozen emergency. A frozen signal in darkness does not equal an easy resource for drinking, oxygen, or fuel. To reach polar resources, machines must cross rough ground, deep cold and darkness without easy rescue. Water matters only if crews can find it, extract it, clean it, and use it reliably. A habitat must become a small artificial ecosystem, recycling air and water while managing every waste stream. Food adds another layer, because biology is harder to ship than equipment and harder to repair. On Earth, a cup of water feels ordinary. On the moon, it becomes strategic material fast. Every spare part launched from Earth carries cost, delay, and risk long before it reaches orbit. The moon makes Earth's quiet protections visible: air, weather, water cycles, and magnetic shielding we rarely notice. Before humans choose a home there, they must decide which location balances science, safety, power, and resources. A lunar base is not one building, but a chain of systems keeping fragile life alive. Outside the airlock, every step depends on machinery, pressure seals, and oxygen the landscape cannot provide. A habitat on the moon works less like a house and more like a carefully balanced machine. Pressure is the first invisible wall, holding human life against a vacuum that never relaxes outside. Oxygen, heat, and electricity must work together, because one failure can quickly threaten everything inside the habitat. On Earth, a broken heater is inconvenient. On the moon, thermal control becomes survival engineering fast. The same sunlight that powers equipment can also create brutal shadows only a few feet away. Solar panels need steady light, but the moon's terrain turns power planning into a moving puzzle. Near the poles, sunlight and darkness sit beside each other, like two different worlds almost touching. A promising base site must balance light, communication, landing safety, science access, and possible nearby resources. That balance is why lunar exploration is no longer just about where astronauts can safely land. Every route across the surface becomes a question of slope, dust, visibility, and possible rescue options. A rover may look simple from far away, yet each wheel must survive abrasive lunar soil. When dust coats equipment, it can block radiators, grind joints, and follow astronauts back inside again. The problem is not one dramatic danger, but thousands of small contacts slowly happening over time. An airlock must become a border between the clean machinery of life and the powder outside. Even the act of returning indoors can drag the moon's harsh surface into a habitat repeatedly. Radiation adds another invisible problem, because the moon lacks Earth's thick atmosphere and protective magnetic field. Shielding may require buried modules, thick regolith covers, or careful use of natural terrain nearby for safety. A future habitat might hide beneath the surface, not for secrecy, but for basic human protection. Living underground would change the dream of lunar exploration into something closer to survival architecture planning. Yet the surface still matters, because crews need sunlight, mobility, landing zones, and open horizons too. Every design choice forces a trade-off between safety, science, power, distance, and human endurance there daily. The moon is close compared with Mars, but closeness alone does not make it forgiving at all. A supply delay that seems small on Earth could reshape every decision inside a lunar outpost. Crews would need spare parts, medical plans, and systems that keep working when Earth feels far away. The question becomes less about planting a flag and more about staying alive after the ceremony. Water could change everything, but only if future missions learn where it is and how it behaves. Detected water is not the same as an easy tank of fuel, air, or drinking supply. Before using lunar ice, explorers must understand its location, purity, depth, texture, and long-term stability first. That uncertainty keeps the South Pole important, because resources and risk may occupy the same shadows. A base built near possible ice would still need roads, power lines, and reliable communication paths. The moon asks for infrastructure before comfort, and infrastructure depends on science still being tested carefully. Even landing heavy cargo creates danger, as rocket exhaust can blast dust across fragile equipment nearby. A future base may need landing pads before it can safely receive the machines to build more. Each solution reveals another dependency, turning settlement into a network rather than a single heroic achievement. This is why living there is not just engineering, but an investigation of the moon itself. To survive long-term, humans must learn how the terrain, dust, cold, and resources actually behave together. The old image of a simple gray world gives way to a working landscape of hazards. Yet that difficulty is exactly why the moon matters as a test before deeper space travel. If we can understand this nearby world, we may learn how exploration becomes sustained human presence. The moon could become a laboratory, a proving ground, and a mirror for Earth's ambitions in space. But every future plan still rests on unanswered questions buried in dust, shadow, and old rock. The nearest world beyond Earth is close enough to reach, yet complex enough to humble us. Before the story ends, the camera has to return from future plans to the sky above home. Back on Earth, the moon looks familiar again, hanging quietly above rooftops and evening streets tonight. Through a backyard telescope, the same bright disk becomes a question rather than a finished place. A small eyepiece opens into craters, shadows, and histories far larger than the neighborhood below us. All these mysteries connect, from ancient impacts to water, dust, quakes, and the question of survival. The moon still asks whether reaching a world is the same as truly understanding it at all. From this distance, the moon looks close enough to know, yet far enough to keep asking questions. Orbital maps reveal patterns across the surface, but every scan still leaves places waiting for ground truth. Even a few grains of lunar dust remind us that small details can shape an entire mission. Water signals changed the old story, though they did not turn the moon into an easy reservoir. In the polar shadows, possibility survives because sunlight has failed to reach some craters for ages. The far side is not dark, but it remains separated from Earth by geometry and silence. Fault scarps crossing the surface show a world still adjusting, even without Earth-like plate tectonics below. Every unanswered clue points back to the same lesson: the moon is simpler only from a distance. For future explorers, uncertainty is not a flaw in science. It is the terrain they must cross. The story now turns from what we wonder about to what humans must solve before staying. A habitat begins with shelter, but survival depends on power, heat, pressure, and constant maintenance every hour. Solar panels can drink sunlight on crater rims, while darkness nearby may hide resources in cold traps. Rovers may travel miles across gray plains, yet one rough slope can decide where people safely go. Each landing stirs dust, throws debris, and reminds engineers that arrival itself can reshape the worksite. A future outpost would need to read the moon constantly, not simply stand on it and wait. That means every sensor, cable, and rover track becomes part of a larger scientific conversation over time. The moon is close compared with Mars, but close does not mean forgiving, simple, or safe. Living there would feel less like camping and more like maintaining a small island in space. Each practical system leads back to science, because what we misunderstand can become the next hazard. Before the moon becomes a destination, it remains a test of how carefully humans can learn. From Earth, the questions become quieter, hidden behind the simple beauty of moonlight over American cities. A backyard telescope can show craters, but not the cold traps, deep layers, or buried history. Museum artifacts remind us that Apollo was a beginning, not the final chapter of lunar science. Launch pads, rockets, and mission rooms all point toward the same unfinished neighbor above the horizon tonight. The moon connects old footprints with future machines, turning memory and planning into one long investigation. Every new mission adds detail, but the larger picture changes slowly, like a map gaining texture. The question is no longer whether we can reach the moon, but whether we can understand it. That understanding may help protect future explorers, decode ancient impacts, and prepare for deeper journeys outward. The moon also reminds us how much Earth has erased through weather, oceans, and moving crust. Its silent surface keeps records our own planet could not hold onto for 4 billion years. So the nearest world becomes many things at once: archive, laboratory, mirror, destination, and quiet warning. It is not mysterious because science has failed, but because science keeps finding better questions to ask. Some answers will come from orbit, some from samples, and some from boots touching new ground. Others may wait in darkness so cold that time itself seems to slow inside the crater. When Earth rises over the lunar horizon, the whole investigation turns back toward where we began. Reaching the moon was a milestone, but arrival never meant the end of understanding its story. The world above us is partly known, partly waiting, and close enough to keep calling us back. The next time the moon rises, it may look familiar, but the story is still unfinished.